So we're back to section 5.3 after doing 5.6 and 5.7. And in the next two sections, we're going to talk about rational functions. So first, we'll talk about the properties of rational functions, and then we'll graph rational functions in section 5.4. So today, let's talk about the different things. First of all, what makes a rational function? So your book defines a rational function to be a function in the form of p of x over q of x, where p of x and q of x are polynomials, which is why we wait to do this after all the polynomial stuff. Please note that the denominator can't equal 0. So that's a rational function. Now we've already discussed the domain of rational functions, so let's do a quick review of that. So in example 1, part A, we see a rational function, and it says g of x is equal to 6 over x plus 3 times the quantity 4 minus x. So this is a rational function. It's got a polynomial on the top. The polynomial that is in the numerator is just a constant function that is still a polynomial. The denominator has a factored polynomial of x plus 3 times 4 minus x. Now we know that the denominator can't equal 0, so the domain is addressing that fact. So we're going to recognize that x cannot equal a -3. If you plug in a -3 to the first factor, you'll have 0, and 0 times anything is 0, creating 0 in the denominator. Not good. We also recognize that x can't equal a +4. That's from the second factor in the denominator. Plugging in 4 gives us a 0. No zeros in the denominator. So our domain then has to avoid these two numbers. So -3, we'd have an open circle, and at 4, we'd have an open circle. And then you cover everything else. So the domain would actually go from -infinity to -3, from -3 to 4, and from 4 to infinity, and that's our domain. And we did this clear back in chapter 3, where we talked about functions for the first time. So we've done this before, it's not new. Part B is the same type of problem. It's asking us to find the domain of this rational function. R of x is equal to -1 times 1 minus x, all over the quantity 3x squared plus 5x minus 2. So notice the polynomial in the numerator. The denominator is the issue though. This time it's not a factored polynomial, but we can factor it fairly quickly. So take a second and factor it. You'll end up with 3x minus 1 and x plus 2. So we know that x cannot equal a +1/2 and x cannot equal a -2. So on your number line, -2 will have a hole and a +1/2 will have a hole. So now write your domain. We go from -infinity to -2, and -2 to 1/2, and 1/2 to infinity. There's our domain. But what does this information do to the graph of a rational function? So we're gonna have some conversations, but let's deal with something that's a little bit simpler as a rational function. So we're gonna backtrack and look at f of x is equal to, we're going to do x over x minus 2. So where is this function undefined? Well, it is undefined at x equal to 2. So we know that the domain would go from -infinity to 2 and from 2 to infinity. So the question is what happens to the graph over here when x is 2? What happens if we can't cross that? What do we do instead? So what we're going to do is we're going to build a table, and we're going to investigate what happens as we get closer and closer to 2 from both sides. So we're going to come in and approach 2 from the left side, and then we're going to come in and approach 2 from the right side and see what happens to it. So we'll build a table. The graphing calculators are wonderful at doing this. So we're going to plug in 1.5. Notice that's to the left of 2. Then we're going to plug in 1.9, which is a little closer to 2, and then 1.99, and then finally 1.999. What we're doing is plugging 1.5 in for each of these x's and evaluating that. And if we do that, when we plug in 1.5, we get a -3. So at 1.5, we're clear down here at -3. So we have a point, right? We're not plotting the point, but just to get an idea. When you plug in 1.9, you actually get -19. So now I'm closer to 2 over here at 1.9, but I'm way down here at -19. If you plug in -1.99, even closer to that value of 2, you're going to get a -199. And finally, if you plug in 1.999, you get -1,999. So what we can conclude is this, that as x approaches 2, and then you're going to see a little plus sign after the 2, and it looks like it's written as an exponent. Well, what this means in mathematical language is that we're approaching 2 from the right side. So that plus means from the right. So this is coming from the right. we can say that the function is approaching what? Well, these numbers are getting more negative. So if I plug in 1.9999, we're probably going to get negative 19,000. This thing is approaching negative infinity. So this thing is headed down. So the graph is doing something like this as we approach to from the left side. But what about from the right side? So now we'll come in and do the same thing again. We do x and we'll do f of x. But this time we're going to come in from the right side. So we'll plug in 2.5 as our first number. And we're going to plug in 2.1, 2.01, and 2.001. So notice we're coming in from this side this time. What's happening? When you plug in 2.5 this time, 2.5 over 2.5 minus 2 comes out to be 5. So at 2.5, we're up top. We're up here somewhere. When you plug in 2.1, you get 21. When you plug in 2.01, you get 201. When you plug in 2.001, you get 2000. So what's going on is that this thing is headed up. So the graph is coming in and doing this shape. So we know that as x approaches to from the, sorry, I did that backwards. I need to correct myself. You probably are screaming at the video already. Let's make sure we get our left and right correct. That's my dyslexia problem. So this guy, we're coming in from the left side. So we're approaching it from the left. So that should have a minus on it, which it does on the handout. This guy is coming in from the right. So it's coming in from the right-hand side. We can say that f of x is approaching positive infinity. So on the left side, as we come in from the left, it's going down. And on the right side, as we're coming in, it's headed up. So the conclusion is there in the box. And it simply says that as x approaches c, where c is a constant. So in this case, c was 2. Then the values of the rational function either head towards positive infinity or negative infinity. And it doesn't always mean the left side is negative infinity. It does not mean that. That's just the example we put. It could have easily just gone up on this side and down on this side. It could have also gone up on both sides. So it just means that it's approaching infinity as we approach that constant. This means the line x equal to c is a vertical asymptote. And asymptote is a new word for us. It's asymptote. So it is not a English language or an English term normally. So asymptote, get used to it. The graph of the rational function will never, ever, ever touch that vertical asymptote. So that imaginary boundary line that is drawn right through it too on this picture, we are never, ever going to cross. And that is the vertical asymptote at x equal to 2.